Hello, everyone, and thank you for joining us today. I am your host, Shannon, and welcome to the webinar, How to Obtain Fast and Accurate Results for Any eDrive Test. Now, before we begin the presentation, I would like to review a few housekeeping items with you. Please take a moment to observe the tools in the WebEx event window. All attendees' microphones are muted during the webinar. Please activate your PC speakers to enable audio or connect headphones to your PC. Please type any questions you have using the Q&A dialog. You can open the Q&A window by selecting the Q&A icon at the top of the WebEx toolbar. Today's presentation will be emailed to all attendees. The webinar will also be posted on our website. For additional questions, please contact technical support at support@usa.hvm.com. Now, today's webinar will be presented by Mike Hoyer. He is one of our application engineers. He's been with the company for over 30 years. He has a bachelor's of science in electrical engineering, an associate degree in engineering science, and over 35 years of radio broadcasting experience, with also 30 years of data acquisition and application engineer experience. I will now like to welcome Mike Hoyer to begin today's presentation.
Well, thank you very much, Shannon. Can you hear me okay?
I can hear you great.
Sounds great. Well, welcome. Glad to have you along. And today's webinar, it's entitled How to Obtain Fast and Accurate Results for Any eDrive Test. So I say any eDrive test because I guess when somebody thinks of eDrive, they may think of maybe just a vehicle or a car or some type of transportation. But it could also be an electric drivetrain that's involved in maybe many other applications, whether it be a drilling tool or a washing machine, a forklift. So there's many applications, and they're ever growing every day. So here's the agenda for today's webinar. We'll just briefly work our way into what is an eDrive test. We'll talk about how to obtain fast results, and this is the exciting part, how to obtain fast results through a dynamic power measurement. We'll talk about raw data storage and analysis, real-time results and integration, and then we'll talk about how to obtain accurate results, touching on accuracy and measurement uncertainty, accuracy, and the type of inputs and sensors, because there's many types of inputs you can consider in addition to the traditional voltage, current, torque, and speed. You may want to consider things like vibration, temperature, and CAN, and things like that. And then we'll wrap up with a conclusion where you can get some additional information and some links and things like that. So we'll start with what is an eDrive test? Well, basically, what is an electric drive or eDrive test? Basically, the elements of an electric drive or eDrive system would include a power source. It's often a battery or DC bus. Sometimes it could even be AC. A power converter, basically most often an inverter changing DC power to AC power. And then you have your motor at the end there, using AC power to convert electrical energy to mechanical power. So just to make sure we're all on the same page, what is the eDrive testing goal? So basically to maximize efficiency across the entire electric drive system. And how do we do that? Well, we want to maximize the torque per amp by using techniques such as clever battery, inverter, or machine designs, and by implementing appropriate control techniques. And to accomplish that task, there's a lot of testing that needs to be done. You need to measure, you need to analyze, gather as much information as possible, and at the highest accuracy, especially when you're improving efficiency. So how do we go about measuring and analyzing an electric drive system? Often one will use a power analyzer, basically a test instrument for measuring the power flow in electrical systems. Could include power generation, consumption, loss, efficiency, and traditionally measuring voltages, currents, torques, and speeds, etc. It's used in many applications. However, there's no universal solution to every power measurement challenge. But why do we measure power? Well, basically, we want to improve efficiency and performance of products and services. And we want to be able to minimize the loss and consumption resulting in reduced costs. We want to also extend the length of time or travel that an electric drive can provide. We want to avoid downtime and revenue losses by determining the origin and type of power issues. And we want to ensure safety of products and, of course, operators and comply with industry standards. So how does one make measurements accurately and minimize measurement time? Well, naturally, we want to measure the efficiency of a motor or of an electric drive. It's going to require massive amounts of testing time at many different conditions of torque and speed to create efficiency maps, which sometimes can take hours, can take sometimes weeks. So it's a good point to be able to identify how one goes about improving the speed, as well as the maintaining or improving the accuracy of that measurement. But first, we want to talk about some time-based calculations versus cycle-based calculations, because this is the key point about how one goes about improving the speed of the measurement. So we'll start with the AC signal. It's primarily characterized with a RMS calculation, and that can be based on time or cycle. So let's just quickly review a fundamental measurement. At the RMS calculation, if you're basically measuring on time, it could be a random non-integer number of cycles, doesn't always produce a correct result. But if you're measuring based on cycles, it's an integer number of cycles. You're always providing an accurate result, something also known as true RMS. So if we take a look at the diagram here, at the top we see an example of an AC sine wave, could be current, for example. In the middle, we see two square waves, which show the length of time or the period when the RMS calculation is going to be performed. So the top or black square wave is created based on a randomly chosen amount of time. Could be something that is designed by the manufacturer, or maybe you had the capability of entering the amount of time that you want to perform the calculation on. But now on the bottom or red square wave, we have what we have created there. It's based on the zero crossing points of the AC sine wave. So to show you a little bit more what this looks like, I've added some letters and some numbers here. So basically on the bottom waveforms that we are looking at, we see two RMS calculation results. So what we see on the black waveform result, we see a changing signal because the calculation is based on different fractional portions of the AC waveform, producing an inaccurate result. For example, points between, let's see, points 1 and 2, just eyeballing it, it looks like maybe a cycle and a third instead of an integer number of cycles. Whereas the red waveform, that result calculates the same synchronous portion of the AC waveform. So between zero crossing points A and B, as you see in the small letter A and B, those are basically I'm depicting there the zero crossing points of that waveform. Likewise, it produces the square wave that you see, which is labeled with the capital A and B. It's basically in sync with the cycles of the top sine wave in the diagram. So in this case, you're basically calculating on an integer number of cycles, producing a proper and accurate result. So let's go on to our next topic, where it gets a little bit more exciting on how to obtain fast results through dynamic power measurements. So that's pretty much the key to producing fast and accurate results through the use of a dynamic power analyzer. And what do I really mean by that? Well, first we'll start out with what does a conventional power analyzer do? It performs an analog PLL or phase lock loop based calculation. So it really was designed for steady state or electric grid power measurements, where the frequency is pretty much steady at or 50 hertz or 60 hertz, whatever the grid frequency may be. And it's, relatively steady. And so it's able to make those measurements quite nicely. But it only works in a steady state load condition. So the traditional or conventional power analyzer was never designed for pulse width modulated motors or variable speed drives. Hence, when the frequency does change due to load conditions, no results are produced until that frequency becomes stable and static once again, and you got to wait a few seconds before it can then make the calculation. Hence the dynamic power analyzer coming to the rescue, if you will. It detects cycles in real time using advanced digital algorithms. And so you have power calculations that can be performed every half cycle or every full cycle or whatever multiple number of cycles you desire. But the results are provided continuously and accurately because you're looking at the zero crossing points, for example. And even during dynamic load changes, whether you're going up a hill, down a hill, the speed of a drill is under a load and the speed of the drill is changing up, down, whatever type of load condition you may have on the electric drive. And so during those conditions, results can be provided continuously and accurately. And we have a couple of diagrams showing this. So showing that here, we see a current trace on the left, which is in green. And that's used for, let's say, the cycle detection. Maybe that's a noisy current waveform on one of the phases coming out of the inverter. And so what you see in the lightly red waveform there is a square wave. Basically, that's just showing you the zero crossing points on that waveform. And that's used as a basis for calculating the RMS. But on the right side, we also see a similar waveform here in blue that, for example, could be current, once again, from an inverter on one of the phases of current. But you can see it's increasing in speed or in frequency, depending on the type of application you're using the motor on. And the eDrive cycle detection is working even during the startup of this particular frequency, or it could be for example, a bike, or it could be a drill, or whatever the case may be. So even though you have this increasing frequency or speed, you're still able to continuously identify the zero crossing points of the waveform, which comes in handy in order to make calculations. So using cycle detect enables you to do measurements even as the fundamental frequency is changing. So here's an example of a vehicle acceleration from, let's say, 0 to full speed. The top signals include the 3 phases of current, plus the cycle detect signal. And in the middle are the 3 phases of voltage. And on the bottom are the values calculated for every half cycle for active power, reactive power, and apparent power. So using cycle detect enables measurements to be calculated continuously even as the fundamental frequency of the current is changing. So that enables you to do characterization in real-world scenarios, whether it's accelerating, decelerating, increasing in load, decreasing in load, and even develop efficiency maps significantly faster. More on that in a moment. That's where it really gets exciting. So to improve accuracy as well, you want to be able to make measurements on electrical and mechanical power accurately on the same cycle. So cycle detection allows you to do that as well. So you can avoid those greater than one efficiency results. So to produce fast and accurate results, cycle-based calculations are really necessary. And it comes in very handy during efficiency mapping. So having accelerated machine efficiency mapping is a significant advantage on a power analyzer because it can save hours of time, can save sometimes days, sometimes even weeks, and it can be achieved with this cycle detect. In this case, we'll just say you're looking for zero crossings. So the traditional power analyzer needs quite some time to settle on a changing fundamental frequency to deliver stable results. And the typical time frame for one set point could be as much as one reading or every 10 seconds. So cycle detect can compute results every half cycle, for example, easily completing a set point in less than a second. So in this example, we have 280 set points, which includes 20 different speed values as seen in area A. And then what we have is 14 different torque values for each speed step as seen in area B. So for each set point, a 1 second recording is performed, and then a 100 millisecond pause to move to the next torque step and onto another measurement. So after an entire torque ramp, there's a few seconds pause to proceed to the next speed step, and then onto the next set of torque steps. So the entire efficiency map is done in about 8 minutes, whereas the typical power analyzer would take at least 10 times longer due to the 10 seconds settling time between changing of frequencies and added wait time for the motor to cool down, because the motor is going to be running for a longer period of time. So hence this accelerated efficiency mapping saves expensive test time, especially lab time. So let's take a look at an example here.
Has started.
So what we have here is an example of an efficiency map. It's got, I believe in this case, in this example, about 160 set points that are performed in about 80 seconds. So you can set up any type of an efficiency map and table, for example, for creating a map for inverter efficiency, maybe motor efficiency, or even efficiency of the entire drive. And then you can set up the efficiency table with any results that you would like and have them stored to a separate, let's say, CSV or XML file, for example. In this particular example, we have torque, speed, and efficiency. However, you can add additional parameters to the table if you'd like. And so, as you see streaming along here, we've gotten up to over 100 set points already. And we're listing in the first column the torque, the middle column the speed, and on the right column the efficiency that's being calculated. And once it's done here, it takes about 80 seconds for this particular example to produce 160 set points. You'll have a complete table that you can take a look at or bring it into MATLAB for further analysis. And
the acquisition is complete.
There you go. So just an example of an efficiency motor mapping that's done in real time. And that's quite exciting. A lot of times when I've mentioned this to past traditional power analyzer users, they're quite enamored because of the quickness of this particular analysis function. So
the acquisition has started.
Now let's go on to raw data storage and analysis. And here we have a power analyzer that enables us to store the raw signals, because most power analyzers do not store raw signals. And ideally, you want to be able to do recording of the raw signals, and you want to do that at a high rate, let's say 500 kilosamples, maybe 1 megasample, and maybe even up to 2 megasamples if you deem it necessary on each channel for an extended period of time. So having the recorded signals gives transparency to your measurements. You don't just get a power value, you actually get the raw data that went with it. So in fact, storing raw data gives, it's going to save you time and money, since it allows you to easily and quickly audit your measurements. You can go back and recalculate, you can validate your power results, and even do a deep dive into your control algorithms and allow you to correlate tests to models at any time without having to run the entire test again, which can take up costly lab time and resources. So it's important to have also public formulas, as you see here on the bottom right. So it's just another way to audit your measurements. You also want to have the ability to create your own custom formulas, ideally calculated in real time and for post-examination for advanced analysis. So here we have some examples of the automatically created calculations that can be made in a power analyzer using cycle detect. So we see the cycle detection formula at the very top. So the cycle master out is the cycle detect signal, which is the result of locating the zero crossing points on the first phase of current. And then all the remaining calculations that you see below there, just showing here a few examples of some of those equations. We have the RMS current, the RMS voltage, true power, mechanical power, all the way to efficiency. They're all referenced to the cycle-based signal cycle master out, which means they're all calculated in sync or calculated on the same cycle. And then here's a picture of some of the computed waveform results from those calculations. Actually, in this example, I applied a load using a bike brake on a drivetrain. So I just pressed the brake 4 times over a 50-second time frame. And so we have the mechanical power P mech. It's in the top section with torque M and the speed N that's overlapped at the top. And in the middle section, you can see the total apparent power S and the total active power P. And then the machine efficiency is in the lowest section there. So having these results displayed over time compared with the raw data, it's going to enable you to provide further analysis of the inverter characteristics. So now a power analyzer should also offer a variety of ways to either select from pre-configured setups or even allow you to make custom configuration and automatically create all the necessary power flow and power calculations based on your system's configuration. So in this example, you can choose between a basic mains or DC or machine to 3 to 6 phase machines, motor or generator setups, and DC or inverter powered e-axles, or even map your own custom configuration. It becomes a very convenient way to view and understand large systems and saves a lot of time having to create all the power equations because they're automatically created for you based on the configuration that you either select or create yourself. So in this example here, we've got a drivetrain containing a battery source in the middle here in green, and then we have a front and rear inverter plus a front end and rear axle. It's mapped to display the power flow for the measurements. And this in turn simplifies the setup, the display, and the analysis. So basically the power analyzer ideally should provide you with the ability to create custom live efficiency mapping for the inverter, the motor, or you can do that for the entire drivetrain in an effort to more easily optimize each part of the system and the drivetrain as a whole. So essentially you should be able to configure what type of efficiency map that you want to perform or create. Now here's an analysis example of space vector, or sometimes known as Clarke transformation, depending on which side of the pond you're on. But basically you've got space vectors showing a mathematical way to simplify the system from a three-phase system to two entities. So the three currents that you see in the upper left are converted to I alpha and I beta, seen in the lower right. So one signal represents torque, and the other represents magnetic flux. So displaying the two signals, I alpha and I beta, in an XY plot, any unbalance in the control behavior can easily be seen. So I'll give you kind of an example of what that looks like here. By applying the space vector transformation, it's a bit easier to understand what's going on in the machine, for example. So here I'm displaying the two entities, I alpha and I beta signals, as an XY plot. And this shows any unbalance and the control behavior, in this case during an electric motor bike acceleration. So this can be displayed live, or you can play back the analysis after the test since all the data was recorded. So for DQ0 transformation, sometimes known as Park transformation, you'll need the angle of the motor, which is called Y mech here in this example. Now to transform the space vectors to I alpha and I beta into a rotational coordinate system, you can do that through that angle of the motor. So the result is D and Q traces, which are directly a measure of the torque and the flux, and are basically DC values with some ripple. So now the motor can easily be understood, and actually inverters think in DQ0 entities, since this is what they compute, and basically this allows you to compare the calculated DQ0 control measurements from the power analyzer, which can then be streamed to your dyno and compared to your inverter's DQ0 control measurements. So this helps engineers like you develop inverter firmware and understand how well the inverter works with the motor, and maybe decide you'll need to change the firmware to achieve better results to improve the efficiency, especially during control changes. So a power analyzer should ideally offer quite a wide variety of advanced acquisition and advanced analysis applications, such as vibration analysis, CAN-bus correlation, and as we already mentioned, the live DQ0 transformation, drive cycle analysis, dynamic power measurements, transient torque, torque ripple, in vehicle measurements, and even live efficiency plots. Now, these analysis features are made possible by the storage of raw data plus real-time and post-analysis equations, which should be automatically created for you based on the configuration of your drivetrain setup. Now let's talk about real-time results and integration with your control or dyno. So a standard readout after making power measurements may be sufficient for some users. However, engineers need more information, and maybe you need to visualize the data, maybe perform custom calculations or generate results in real time, and often perform many numerous analysis functions, including efficiency maps and so on. So you want to be sure that the power analyzer that you're using can provide full data transfer to automation systems with refresh rates for, well, at least 500, sometimes 1,000, maybe even up to 2,000 results per second. This means that your dyno, aka the automation control system, will get results when needed. So the real-time feedback and communication with a control system makes the test automation possible, especially when you're developing efficiency maps to record and calculate numerous torque and speed test points, which is the type of testing that's done day in and day out quite often to improve the efficiency of the motor and of the inverter communicating with the motor. And even standard buses, including CAN, EtherCAT, and Ethernet, plus real-time equations combined with a variety of control options, simplify that automation process between the power analyzer and the control system, or dyno. So you want to make sure a power analyzer offers a variety of communication methods and control options for seamless integration. And you want to make sure the power analyzer solution offers a list of system integrators and their customers where the analyzer was successfully integrated into automation systems. And this is just an example of such a list. Now we'll talk about how do you obtain accurate results. Talking about accuracy and measurement uncertainty, and the accuracy based on the type of inputs you may be considering to capture along with some of those sensors. So measurement accuracy is a fundamental term that you need to basically deal with when you're optimizing the performance of an electric inverter, motor, or drivetrain, especially when you want to improve the efficiency. So by decreasing measurement uncertainty, you can generate more credible results. In fact, best-in-class accuracy provides engineers like yourself with reliable data for understanding how to optimize inverter-driven machines. Selecting a power analyzer with the best base power accuracy available is an investment in the long-term future of your products and your solutions. So you also want to make sure you select a power analyzer with the best torque and speed accuracy. So not just the voltage and current inputs, but also the torque and speed, especially with the ability to use digital frequency signals for noise immunity instead of just trying to capture an analog torque, which often has a lot of noise involved. So you'll need to identify the accuracy of the timer counter inputs on a power analyzer. And what good is the accuracy of your power analyzer if you don't, if you haven't checked that you're using high accuracy sensors, including current sensors, because current can be one of the most toughest signals to capture accurately. And there's also sometimes involved voltage dividers, torque transducers, speed sensors, and so on. So that becomes just as important. So there's no standard definition for electric power measurement accuracy. In fact, every manufacturer defines their own method. Often you may see one banner spec, for example, 0.03% accuracy or measurement error. But then you need to ask yourself, okay, 0.03% of what? I mean, is that of voltage? Is that current, power, DC only or AC? And at what frequency? At what power factor? Or at what input range? Is this with or without averaging, with or without filtering? And is the accuracy specification a pass or fail, or known as a guaranteed spec, or is it just a typical spec and it's not necessarily guaranteed? Well, these are some of the questions you'll need to ask when you're reading a data sheet. So it can get quite involved reading all the fine print. So ideally, a power analyzer's accuracy specification should include accuracy along with quite a number of pieces of information. So for example, here's a datasheet example of a 3-channel power card for a power analyzer. For example, we first have the banner spec 0.015% of reading, which is often the gain error, and then 0.02% of range, often listed as the offset error. So if you're looking to seriously improve efficiency, this is one of the best banner specs that I've seen. Now, the accuracy specifications on the datasheet should be detailed and identify whether they're pass-fail, or if they're guaranteed, or just typical not guaranteed specs. In this example here, we see that the datasheet specifically states pass-fail limits right there at the top. Also, it's good to have more detail, including formulas, tables, like you see here, even frequency plots and specifications over a variety of power factors, frequencies, and even input ranges. So when it comes to measurement uncertainty, it would also be ideal to have examples with formulas, like you see here in this example. We can see the formulas and examples for 2 different power ranges for DC power and RMS power at 10 kilohertz and power factor of 1. And here's a small datasheet example of measurement uncertainty with tables, again, over a variety of voltage, current, and power ranges, and over a variety of frequencies from DC to 100 hertz, 1 kilohertz, 10, 100, 200, and 500 kilohertz for both the reading and the range. Now, it's also just as important to have detailed specifications on the accuracy and measurement uncertainty of your timer counter inputs and torque and speed measurements, again over a variety of frequencies, measurement times, or update rates. Now, all the accuracy specifications are needed on all inputs and all sensors that you're going to be using in your test, so that way you can identify the overall accuracy of the entire measurement. So ideally, you want to select a power analyzer that meets your needs today, and that can also be expanded for tomorrow's applications, otherwise known as future-proof. So, for example, a modular approach means that your power analyzer can be easily expanded with more acquisition modules, offering more power channels and timer counter channels for torque and speed measurements. So, for example, you might start out with an inverter-driven application requiring, let's say, at least 4 power channels. So 3 for the output of the inverter, 1 for the input to the inverter from the battery or the DC signal. Plus maybe you need 1 torque and 1 speed sensor. So let's say you start out with a 7-slot mainframe, and you would need 2 3-channel power cards, and you'd also include timer counter inputs for torque and speed. Well, then maybe tomorrow you'll have a 4 inverter-driven vehicle application, for example. Maybe each having a 3-phase inverter. And then you need at least 13 power channels. You'll need 4 torque and 4 speed sensor inputs. So to expand with a modular system, you just add 3 more 3-channel power cards, which happen to include also 4 timer counters for each torque and speed inputs. So when you're looking to purchase or use a power analyzer, you like to make sure that your investment is future-proof. So here, we're looking at a number of other channels that you may need to record. So in addition to the power card, you have the 3 power channels per card. So this particular card here has 3 voltage inputs and 3 current inputs, with the highest power accuracy of 0.15% of reading and 0.02% of range. The voltages actually can be read directly up to 1500 volts plus minus directly, and If you need to measure anything higher than that, you can go to a differential probe with 0.1% accuracy and measure up to 5 kV. If you need to go to higher voltages than 5K, you can certainly look at some isolation systems. So higher voltages up to 20 kV, including isolation. On the current side of things, which often becomes more difficult to measure accurately, you have, or require, you actually need high accuracy, medium bandwidth, zero flux current sensors. So here you may have ranges anywhere from, let's say, 50 to up to 2000 amps for most of the common applications. You'd like to have some wide bandwidth, maybe up to a megahertz, and some high accuracy, for example, up to 0.01% accuracy to 5 kilohertz. And they're recommended for high accuracy measurements. Otherwise, you want to be able to have the alternative to make an option for a current probe, maybe a Rogowski coil. Even though that's less accurate, they come in handy when bandwidth is more important than accuracy, or you don't necessarily have any room for a CT for that particular measurement. Ideally, you want a sample rate of somewhere around 500 kilohertz, maybe a megasample. Shouldn't need much more than 2 megasamples in rare cases, but you want to have a lot of bandwidth, and you want to have some high accuracy. In this particular case, this card here has 18 bits of resolution. And there's even options for higher sample rates, up to 250 million samples per second per channel. Nice thing here, you see too on the right side on the top here, this particular card also has auto ranging to minimize measurement uncertainty. And that comes in handy when you want to even increase the accuracy on your measurement for efficiency. Some other additional inputs that you may need include timer counter inputs for torque and for speed. Certainly, there may be applications when you can only record analog torque because maybe your torque transducer only has analog output. But ideally, you want to be able to have a torque transducer that produces a digital output because that's going to provide you with noise immunity. So you want to be able to record frequency output from a torque transducer for the highest signal fidelity. Depending on how many electric drive trains that you're performing a test on, sometimes you'll need a number of timer counters. In this example here, we're talking about 8 timer counters needed for a 4-wheel motor measurement. And torque transducers up to an accuracy are 0.007% are available. That's pretty much the highest that's available in a torque sensor. Higher accuracy for higher efficiency measurements is required. So you see 2 torque transducers here in the upper right corner. Some of the traditional measurements, maybe you only need 0.03% for linearity measurements for an accuracy. But when you're really looking to improve the efficiency of an electric drivetrain, you want to strongly consider the highest accuracy available on the planet, that being, again, 0.007% linearity. Maybe you want to make temperature measurements, another common measurement for electric drivetrain test measurements. You may have standard thermocouples, maybe you have RTDs, maybe you need some isolation up to 1,000 volts. So those types of temperature measurements are available. Maybe you need to make some vibration measurements, microphone measurements for NVH analysis. So depending on the type of signals that you need to record, you want to make sure that your system has a variety of options to record those signals. So for a modular system, you can see here, you could have a number of different cards that you would choose from depending on the signals that you need to record. Could be strain measurements that you want to measure multi-axis forces and moments on a particular structure. Maybe you need to record CAN or CAN-FD for bus data from a vehicle, for example. And ideally, you want to have high voltage, low noise shielded cables. So really to provide a full, complete solution, ideally the power analyzer should provide the ability to supply some high voltage, low noise shielded cables for getting your signals recorded with the highest fidelity possible. Well, just before we get to our conclusion, I just wanted to make a quick mention on all the fine specifications presented in this webinar, and they were on HBM HBK products, including power analyzers, power cards, data sheets, torque sensors, CTs, multi-axis sensors, high voltage cables, temperature modules, and all the real-time and post-analysis functions. So just a quick summary on the HBM power analyzer solution designed for electric drive testing. You have here a variety of different mainframes you can consider, anywhere from 2 to 4, 7, even up to 17 slot mainframes, and additional mainframes can be even synchronized together for a single system if you need to go even further and beyond a single mainframe. So in a single mainframe, you can actually have up to 51 power channels. You can have up to 12 torque and 12 speed sensors, and even have fiber optic remote control. Maybe you want to store to an SSD locally on the mainframe itself. Now, the 3-channel power analyzer card we mentioned previously, it does provide you with 0.015% of reading, 0.02% of range accuracy. It basically has 3 voltage inputs that can measure directly up to plus minus 1500 volts DC. And you can also measure 3 current inputs using CTs or clamps. Sample rate is up to 2 million samples per second with 18 bits of resolution. And the card has onboard DSPs so that you can use basically programmable math for digital cycle detection for reliable results. Then you have high accuracy torque and current transducers. So anywhere from 0.03 to up to 0.007% accuracy, which also include a speed option with reference pulse, so you can identify the position of the motor, and a full range of CTs from 50 amps to 2000 amps with a slimline power supply. And then a whole bunch of accessories to complete the solution, everything from EtherCAT and CAN-FD for real-time data transfer, CAN-FD for input for bus data, thermocouple modules, vibration and microphone inputs for NVH, cards up to 250 million samples per second, high voltage probes up to 20 kilovolts, and even high voltage low noise cables, providing really a complete power analyzer solution from one supplier. So in conclusion, how do you obtain fast and accurate results? Well, it turns out for variable speed drives, you need the capability of performing dynamic power measurements, because digital cycle detection enables the measurements during the dynamic load changes, and the digital cycle detection creates efficiency maps in minutes instead of hours. Raw data storage and analysis capability is very strongly encouraged because you can store raw data and not have to go back to the lab and retest. You can just recall the data and then perform some validation and correlation. You have advanced setup and analysis capabilities. That makes it really convenient so that you can set up the system for just about any type of electric drivetrain configuration. And it's going to help you to do some advanced analysis so you can figure out ways and understand how to improve your electric drivetrain system and improve the efficiency. So the real-time results and integration comes in very handy so that you can do the quick efficiency mapping so that it's communicating with your control PC or your dyno. There's a variety of communication methods that are possible. So that option makes it pretty much seamless for integration for just about any type of system. And the accuracy and measurement uncertainty. You want to make sure you're getting the best accuracy so that you have reliable and credible data, especially when you're trying to improve the efficiency. You want to be sure to get the highest accuracy possible. And you want to make sure you read the fine print on those data sheets on the power analyzer and all the sensors as well, because that all becomes part of identifying the accuracy and measurements uncertainty of your entire system. And naturally, you want the ability to have a number of different types of inputs. A modular solution is going to offer you be able to have that also on torque and speed and be able to make measurements for temperature, CAN, NVH, etc. So some additional information here, some links. This will be on the presentation that we'll supply to you, so you'll see the links for getting more information. For example, on the top here, we actually have a YouTube channel which provides numerous videos that you can watch on electric power testing, just about on every possible topic you can imagine. We also have an electric power testing knowledge base available, so you can get information on white papers, customer application stories, videos, and tutorials, and then a whole list of the different pieces of the electric drive testing solution are available real simply by typing in hbm.com/eDrive. Just a quick note, one slide here before we wrap it up. Basically, who is HBK? You may have not heard of HBK before, but basically it's the combination of two companies, sister companies coming together, HBM and B&K. So on the HBM side, test and measurement, fatigue, and reliability and analysis plus custom sensors was predominantly the solution on the HBM side. So measuring more so in the time domain. And then along here on our sister company, Brewin Care, we've merged together where they have been focusing on sound, noise, and vibration, plus NVH engineering services. So together, just a few years ago, we combined together as one company, providing a total solution, integrated solutions for just about any type of test from a signal partner called HBK. So under the HBM umbrella, you've got sensor products for torque, force, pressure, displacement, load cells, custom, conventional, and optical strain gauges, data acquisition systems from low and up to high speed, and even rugged data acquisition systems. And we already mentioned the power analyzers for eDrive. We also have solutions for eGrid, data acquisition amplifiers for industrial control, and a whole wide variety of analysis software for fatigue, structural durability, and reliability. On the Brewin Care side, we've got the sound and vibration analyzers, sound level meters, software for sound and vibration analysis for many, many types of different applications. Vibration systems, including shakers and controllers, and acoustic end-of-line test systems, microphones, accelerometers. So essentially now HBK providing you a complete portfolio of solutions, including engineering services. We can actually, on the engineering services side, we can provide you with a whole solution just about in any type of measurement chain, whether it be at our facility where we have chambers and all different types of test equipment that we can perform on our site, or we can come to your site and provide you the solution and teach you how to perform the testing as well. And that comes in very handy so that you can, going forward, do the testing yourself. But anytime you have questions, just let us know. So this really means shorter development cycles in optimized products and better decisions. So that wraps it up for the webinar on basically trying to improve the speed and accuracy of your eDrive tests. And now we'll open it up to some questions. Shannon, what do you have?
Awesome. Thanks, Mike. Yep, at this time, please enter your questions in the Q&A panel. Another reminder that today's presentation and a copy of the slides will be emailed to you. Be sure to also, upon exiting WebEx, take the survey as well. Let us know your feedback on what you learned today and what you would like to see in our other webinars. Let me check and see what questions we have here. Okay, let me see. Mike, is it possible to create a custom analysis equation that calculates and displays a result in real time?
Yeah, great question, Shannon. Actually, the simple answer is yes. Actually, you can create a custom equation and display the result either as a waveform, or you can display it as a numerical result, either in real time while the test is going on, or you can even do that as a post-analysis calculation on the raw data afterwards, whether it be later in the day, next day, or next year. and or any time in the future. So that actually becomes one of the strong possibilities and capabilities of the system.
Great, thank you.
All right.
And one question here, can efficiency mapping be automated, and how can it be automated?
Well, that's an interesting question. Yeah, I mean, simply the answer is yes. Actually, I think I can pull up a diagram that shows how the process works. Let's see. See, there we go. Here we go. So here we have kind of a flow chart of how efficiency mapping works on the system in conjunction with your dyno or automation system. So you can actually set up the dynamic power analyzer to capture multiple sweeps. So actually the number of sweeps would correlate with the number of set points that you're going to perform, which could be anywhere from 50, 100, several hundred, or thousands. And you can decide on how long you want to capture each sweep. Could be quarter second, half a second, full second. It's any time that you prefer to measure for that set point. And then you set up the efficiency map that you want. Could be the efficiency of the motor, the inverter, or the entire electric drivetrain. And you can even set up so that it will display the results in kind of like a log file, basically as a CSV or an XML log file. And you can decide what you want in that log file. It could be torque, speed, efficiency are the common ones, but it could be anything else that's calculated as well. It could also be in that log file. And then your dyno or automation system can send a start command as a TTL or CAN or API RPC command. Then the system's going to wait for the trigger. And then where you see that red line there from your automation system, you can basically have your dynos, set the electric drive system to a specific torque or speed. So you may start with a particular torque and speed, and then you'll send a trigger to the power analyzer, which can be done via TTL, digital I/O, or CAN or API command. Then the power analyzer goes ahead and records the data, calculates the results, displays the results, and then can send the results back to your dyno and also to a log file. And then the whole process begins also creating an efficiency map. And then the raw data is also stored if you wish. You can select whether to store it or not. And then the whole process begins again if you're going to record another set point. And it just keeps repeating itself. Of course, this is all done very quickly, but that's just an explanation of how that process works. So very nice way of doing a very quick efficiency map with your dyno system.
Great. I have another question here. Will system protect conditions when the motor dies?
Will the system protect
conditions when the motor dies?
Okay, so I guess I'm not understanding the question that fully, but we can certainly converse with the person that sent the question. But essentially, protecting the motor. I mean, you could, if the motor, dies or is no longer working, you can certainly have a signal to, of course, to stop testing. But really, the dyno is the one that's in control of the entire test. We're not offering a solution to control the motor per se, because that's really done with the dyno. But if you can get me the email or phone number of the person that's asking that question, maybe I can have them elaborate a little bit more on that question, and we can figure out the best way to provide an answer to that question.
Sure.
Mm-hmm.
Good. I think that wraps up our time for today.
Right.
Oh, it looks like we may have certain peak torque, peak speed points kill the motor. Yeah. Okay, so he left his information here, so I'll be sure, Mike, to give you that. That way you guys can chat and go back and forth.
Absolutely.
From there.
Great.
Is Mike, your information on that last slide as well, just to put that up for anyone who would like
Yeah,
to
let's
reach
go
out to you with
back.
any
There we go. Yep.
additional information? Perfect. And Charles put in his email as well. So I'll be sure to send that over to you, Mike, so you guys
All right.
can
Sounds good.
talk. Awesome. Thank you again, everyone, for joining us today. On behalf of Mike and myself, we look forward to seeing you at the next webinar. Thank you, everyone.
Sounds good. Thanks for your time. Have a good day.
Bye.